Section 14.2, Bronsted-Lowry acids and bases. So yet another definition of acids and bases. Go check out video problem 80 after you're done with this. So the Bronsted-Lowry definition is a little more broad. Okay, it includes some more chemicals that wouldn't normally be lumped in with the Arrhenius acid and base. All right, so it's pretty easy. It says that in a Bronsted-Lowry, an acid donates an H+, which we call an H+ a proton. Whenever we're talking about acids and bases, why do we call it a proton? Because a hydrogen has one proton, right, and it has one electron. So when I take away that one electron for it to become H+, all that's left is the proton. There's no electrons there. There's neutrons, but we don't worry about those. Right? So that's why we call an H+ a proton. Right? Now, that's the definition of an acid. Donates, it's a proton donor. Base is a proton acceptor. All right. So the hydrogen ion that it donates, it won't exist in water by itself. So if there's water, it actually forms what's called the hydronium ion. Now, hydronium ion and hydrogen ion, for me, with acids and bases, is interchangeable. So you'll see that the text sometimes in the notes sometimes say hydronium ion, but I write a hydrogen ion. Sometimes I write a hydronium ion when it should be a hydrogen ion. They're interchangeable. All right, and it just depends on whether you add the water or not. You add the water, you need to form hydronium ion. You don't add the water, you don't need to form the hydronium ion. Okay, but here's what we're talking about. Here's water, right? Here's the proton. Here's hydronium ion. Right? So if we think about it, in this case, here's the hydrogen ion coming from somewhere, right? Water, not hydronium yet, water is accepting that hydrogen ion. So if water is accepting that hydrogen ion, what does that make water? Well, in this case, it makes water a base, because a base accepts a hydrogen ion. So here, good example with hydrogen chloride, which if it's a gas, we call it hydrogen chloride. As soon as it becomes aqueous, we call it hydrochloric acid. All right. So here's the proton. It's going to go to the water. It's going to leave chloride all by itself, and it's going to form hydronium ion. So the HCl would be the acid because it is donating the hydrogen ion, right? Water would be the base because it is accepting the hydrogen ion. But let's flip it around. Right? Here's NH3. Look what NH3 becomes on the other side. So on the other side, NH3 becomes NH4+. So what did NH3 do? NH3 accepted a hydrogen ion to become NH4+. It gained a hydrogen, NH4, and it gained a +1. So that means that I had to have gained an H+. So what does that make that? Well, if it accepts an H+, that makes it a base. So in this case, NH3 is a base, which is ammonia, common name ammonia. Water. Where did that ammonia get the hydrogen ion from? Well, it got it from the water. So look what water does. Water goes from H2O to OH-. It gave away a hydrogen ion. So that means water in this case is in fact an acid. So look, it was a base up here. It's an acid down here. Something's weird about water, and we'll talk about very specifically what it was. But there you go. Now, let's talk about something that students always seem to have a problem with, and that is a conjugate acid-base pair. And I want to explain this to you so that you understand what it is. All right? Why would I explain it to you so you don't understand what it is? That's sort of a silly statement. I apologize for that. So, a Bronsted-Lowry acid or base is reversible. Okay? And so what I want to do, I want to take a look at this reaction. Right, let's take a look at this. That's HF plus water, so hydrofluoric acid plus water. This is what I'm going to do. I'm going to write, so notice that it goes both ways, right? So what I'm going to do, I'm going to write that reaction two different ways. The first way I'm going to write that reaction, I'm going to do it right here. HF, I'm going to drop the phase symbols just to save space, plus water, okay, one-way arrow. It forms what? It forms H3O plus F minus, okay? So one-way arrow in that case. Now, I'm going to write the opposite reaction. So I did this top arrow, right? I did the arrow to the right. Now I'm going to do the arrow to the left, but I'm going to write it backwards. So here, write this F minus plus H3O plus yields HF plus H2O. So what I did there is I wrote the, the reverse reaction. Right. So now let's identify acid and base real quick. So here's HF. HF becomes F minus, so what did it do? It gave away hydrogen ions, so HF is the acid, right? So hopefully water is the base. Let's see, water becomes H3O plus, it accepts a hydrogen ion, so yeah, water is the base in that case. Okay, so there's the top. Let's look at the bottom. So the bottom is F minus. What does F minus become? Well, F minus becomes HF. So what does that make it? Well, it accepted a hydrogen ion, so F minus is a base, right? H3O plus, yeah? It becomes H2O plus. So it had to give away an H plus, so H3O plus in that case is the acid, right? So in each case, we identified the acid, we identified the base, and the bottom we identified the acid, we identified the base, right? So now, let me put these two together, right? So we got HF plus water, right? So there's that one-way arrow, H3O plus F minus. So that's, that's reaction A right there, right? So now if I do an arrow down below here, I've basically written reaction B, but backwards. Okay? So we identified this initially as an acid, right? Acid, yeah. We identified this as the base initially, right? So there's the base. Now, on the other side, we identified H3O plus as the acid, and then we identified F minus as the base. Oops, I want to use green. Give me green. Base. Okay, so constant, let's look at this one right here. We got a problem because we have one acid, we have two acids. So we say, hey, which one's the acid? We don't know, right? Because we got two different acids. Here's the base. Here's the base. Which one's the base? We don't know because we got two different bases. So that's why we can't just say acid and base. So what we do, if it's on the reactant side, it's acid and base. If it's on the product side, it's conjugate acid. It's conjugate base. Okay? So the acid and base are on the reactant side. The conjugate acid, conjugate base is on the product side. That's all it is. That's all the conjugate acid base is. Now, one thing that you're often asked to do is to give the conjugate acid base pair. So for example, here's HC2, H3O2, which is an acid, okay? Now if I ask you what is the conjugate base of this, or it said give the acid conjugate base pair, we would say that the conjugate base is C2, H3O2 minus, because that's the base form. That's the base form of this acid. I just basically removed an H plus. All right? Now, I said water does something crazy, right? So here's water acting as a base. Right? Here's water acting as an acid. Doesn't say it, but it is. Let's write it down there. So water is what's called amphoteric. And amphoteric means it can act like an acid or it can act like a base. So what are some things that are amphoteric? Well, water, obviously, is one of them. But then anything that has a hydrogen and a negative charge can be amphoteric. So I should say a leading hydrogen. So for instance, H2PO4 minus, right? Because that dude can either accept a hydrogen ion, H3PO4, or it can give away a hydrogen ion, which would be HPO4 2 minus. Okay? So if it has a leading hydrogen and a charge, usually a negative charge, it can be amphoteric. And that's all I got to say about that.